Hi there, welcome back to this channel. In today's video, we are going to be discussing the concept of generator effect of electricity, following our video on motor effect of electricity. Alright, by the grace of God, at the end of this video, I hope to bring about a cordial relationship between you and the concept of generator effect of electricity. Before we delve into generator effect of electricity, we'll have to talk about the concept of electromagnetic induction. Electromagnetic induction. Now, what is induction? Induction means to cause, is that okay? To bring about something, is that okay? Or to bring something to doing something, is that okay? If I say a behavior was induced by something, it means that behavior was caused by that thing, is that okay? So electromagnetic induction is the induction or the induction of current or the induction of EMF in a system such as a solenoid, for example. Now this is it. In about 1845, Michael Faraday carried out several experiments, because of the link that had been discovered to be between electricity and magnetism. Remember, by Hans Christian Ørsted in 1820, and since it had been discovered that a current carrying conductor had a magnetic field, that is, current generated electricity, so it made sense to say that electricity could generate since electricity could generate magnetism, rather, electricity generated magnetism, that is, in a wire that had current flowing through it, there was magnetic field around it. That was what we saw in 1819 to 1820, according to Christian Ørsted. And so because of that, it made sense to say that the magnetic field could also generate electricity. Is that okay? If electricity could generate magnetic or magnetism. All right. Now, because of this, several experiments were carried out, and one of which was carried out by Michael Faraday. Now, one of what he did was to use a solenoid. So recall that in this series, we have been discussing a lot about solenoid, okay? Now, what he did about a solenoid was that after bringing the solenoid, he put a magnet close to it. So with a magnet close to it, and he wanted to see if there was going to be current induced in this solenoid. So what he did was this. Now, he brought Now, initially, he didn't know that a stationary magnetic field and a stationary solenoid created no induced current. So he saw that current was not induced. But he now noticed at the end of his experiments that it was a changing magnetic field or a changing magnetic flux that created what? EMF or induced EMF, or that induced current in this solenoid. I repeat that. He finally discovered in 1845 or 1847 or thereabouts that it was a changing magnetic field that induced what? Current or induced EMF in this system. So what did he discover? He discovered that, so one of what he did was he used a loop of wire. So if this was the loop of wire, now he brought a magnet. And you know that magnetic field lines, let's say this was the north and this south. And you know that the magnetic field lines is going to run outward in this way and inward in this way, right? In this direction. Okay, if this was the case. So he discovered that it was when he brought this magnet down and up at a particular, speedily actually, it was when he brought this magnet up and down speedily that current ran through this system, and the direction of current is very germane. Is that okay? He discovered that, for example, in this system, if he brings the north if he brings this north in this direction, the current is going to run in one direction, and if he took it away, he discovered that he took it away, the current flowed in the opposite direction. But the first thing he had found out was that a changing magnetic flux created what? A changing, brought about an induced current. Okay, so I'm going to talk about the direction of current in a jiffy. But first, let's understand what he did here. Now, he discovered that if he brought the magnet, for example, if this magnet now is brought close to this guy, if the magnet is brought close to this guy, force, you know that we said it's a changing magnetic field, and the speed matters also. So if he brings it close in this direction, a current will be induced in this system, and that current will cause this galvanometer, this is a galvanometer, to deflect in the direction of flow of current. The galvanometer always deflects in the direction of flow of current. So if he brings this guy this way, the galvanometer will deflect in this direction. And if he takes the guy back, the magnet back, the galvanometer will deflect in this direction. I hope that is clear. So if that is the case, what happens is that a change in magnetic flux, so that this solenoid is cutting through, resulted in an induced current that caused the deflection of the galvanometer. So he found out that if this body was stationary, this magnet was stationary, there will be no deflection of the galvanometer because no current will run through. And if you moved only the solenoid at a great speed, but then you bring it close to this magnet, galvanometer will deflect in this direction. If you take it away from the magnet, galvanometer will deflect in the other direction. Okay, or this one was stationary and you move to the magnet. He also discovered the word deflection. So it happens that it is when there is relative motion between this body and this body, relative difference in motion. So that is when there is a deflection in the galvanometer. Definitely what that is saying is that if they were moved at equal speed in the same direction, what would happen is that there will be no deflection still. But if there was a difference in the speed of these two guys, such that this one was stationary, for example, and this one was moving, there will be a deflection of this galvanometer. Is that okay? Now, the direction of this deflection will become clear in a jiffy. But before that, let's understand the concept of magnetic flux. Magnetic flux. Now, magnetic flux is denoted by phi. Now, magnetic flux simply refers to the entire group of magnetic field lines that are entering into a particular, maybe entering into the loop. Is that okay? The entire group of magnetic flux. So, for example, the magnetic flux here is just 3. So, what 3 means is 3 magnetic field lines. Does that make sense to you now? Number of magnetic field lines refers to what? Magnetic flux. Is that okay? So, if you recall that we have said that the strength of a magnetic field, we said that the B field strength or magnetic field strength is denoted by B. Is that okay? So we said B is equal to magnetic flux over area. Now, we said with respect to the angle between the normal to this surface and the field lines. Is that okay? With respect to the normal to this surface and the field lines, the angle there brings about a cos theta, so that the closer to perpendicular this thing is, the lower the lower the area in which that thing is cutting, in which that magnetic field lines are cutting, but the higher the magnetic field strength. Is that okay? Okay. Now, so my point is this, that as this guy tends towards 0, as this theta tends towards 0, not becomes 0. If the theta becomes 0, yes, if theta becomes 0, sorry, this is going to be highest. The magnetic field, the area is going to be highest, and because of that, magnetic field lines is going to be less. Is that okay? Magnetic field strength is going to be less, but the closer to 90, the closer to perpendicular, as I said, rather, the closer to perpendicular this theta is, the closer to perpendicular the theta is, the lower the area that will be touched. Is that okay? The lower the area on this field that will be touched. You see, for this my diagram now, you're going to see that the area, the flux is higher because the area in which that is cutting through is much. Does that make sense now? So I said that the closer to perpendicular this theta is, the lower the area and the higher the magnetic field strength. Because it is in that direction that the flux will cut through the wire so much, or the wire will cut through the flux so much. Flux simply means the aggregation of these lines, these field lines. All right. So my point here is that phi is going to be what? BA cos theta. I hope that makes sense. BA cos theta. Okay. Now, in that 1845, this guy Faraday discovered this concept, and he postulated the electromagnetic he postulated what we now call the Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. So Faraday's law of electromagnetic induction states that the EMF induced in a coil of wire or in an electromagnet is directly proportional. So let me put that in mathematical concept, that the EMF induced, EMF induced, is directly proportional to the rate of change in magnetic flux. So it's directly proportional to the rate of change. So what is rate of change? d phi dt. Does that make sense now? d phi dt. So, and you know that d phi refers to the number of magnetic field lines cutting through it, right? So that becomes n d phi dt. Does this make sense now? N d phi dt. Okay? Now, so what that means is that the lower the magnetic flux, the lower the EMF induced. The higher the magnetic flux, the higher the EMF induced. Is that okay? The lower the magnetic flux, the lower the EMF induced, and the higher the magnetic flux, the higher the EMF induced. Okay? And of course, the relative motion, the speed at which that one of those bodies, whether it's the electromagnet or the guy or the magnet is moving, also determines the what? The EMF, the value of the EMF induced. Now, another guy came, Lenz. Lenz found out the concept of back EMF and eddy currents. The concept of back EMF, that was what Lenz basically postulated. And his law was a refining of this law, that the EMF that is induced in this system is always flows in a direction that generates a current that opposes the motion that produces it. Let me recreate that. Let me state that again. The EMF that is induced in this system is going to be such that it opposes the change in magnetic field that produces it. And what I mean is that since EMF is generated, you know current will be generated. So follow me. The moment, what Lenz is saying is that the moment this guy, this north, flows through here, the current for this guy, you know I said this guy will deflect in this way. It means that current is flowing in this direction, isn't it? It means current is flowing in this direction. So let's see if that law has actually been proven. So this is it. As this guy comes in this direction, current is flowing here. This guy will become a magnet, we know, since the current is flowing through it. All right. So if current is flowing through it, it means that here, current, if you look from this side, current is going to be flowing in the anti-clockwise direction. Do you remember? I told you that this clockwise, remember, S clockwise, and north anti-clockwise. Because this guy will go like this will go like this, anti-clockwise. This guy will go like this guy will go like this, clockwise. Does that make sense? So the angle from which you look at, and the current seems to be flowing in the clockwise will be your south. The side from which you look at, and the current seems to be flowing in the clockwise direction, the anti-clockwise direction will be your north. All right, let's go back again now. So the moment I bring this guy here, close to this electromagnet, the current will flow in this direction, which means that the current from here is flowing in the anti-clockwise direction. If current is flowing in the anti-clockwise direction, that will be what? North. So it means this place will be our north. That definitely means that this will be our what? Our south. So let's look at it. That this north has been brought close to this place. What happened? A north is induced here. If a north is induced, then what happened? There's a repulsion. So it has proven Lenz's law that says that the induced EMF creates a current that opposes the change that produces it. The moment you bring this guy to the back, the current will revert, turning this place to a south and bringing this place into, making this place a north. Does that make sense? So there will be a repulsion, there will be a kind of repulsion here that want to oppose the change that is producing it. Is that okay? So that's what Lenz's law is saying. So the refined form of that equation now becomes E equal to minus d phi dt. N d phi rather, minus n d phi dt. So let's now do some mathematics. Let's do some mathematics. So let's put this here. We already know that phi is equal to BA cos theta. Okay, so E is equal to minus n d phi dt. So let's call this equation 1, we'll call this equation 2. Recall that phi is all of this, right? If phi is all of this, therefore E will become minus n d phi. What is the phi now? D NBA. dBA, okay, rather, because phi is not the theta, please. Phi. The phi, okay? So d phi this theta, this phi. So this phi is BA cos theta. Does this make sense? All over dt. Okay? So if this is the case, then we can now differentiate. Is that okay? Let's differentiate with respect to t. So E will now become n minus n d this. Remember that theta, recall that theta is equal to omega t. So if that's the case, this thing can also become d dA cos omega t over dt. Now, by the time I want to differentiate, these are constants. So what do? They remain the same, they don't change. So they come here. So E now becomes minus NBA d cos omega t dt. Okay, so let's differentiate omega t. So d cos omega t, let's differentiate this dt with respect to t. By the time you differentiate this, let's make u equals omega t. If you don't understand the concept of differentiation, do want to see one of my videos on this concept of differentiation. So you differentiate this with respect to t. What happens? We are going to get omega, because omega is going to be a constant there. So you have du dt is going to be what? Omega. So, and it means that our derivative has become d cos omega t is now u. So let's have this. So by the time you differentiate this du, you differentiate cos u, you're going to get minus sine u. So if that's the case, you now have, yes, it's exactly the same thing. It's just I didn't equate this. So if our function was y equal to this, and our function here is y equal to this, so it means that what we're doing is basically this, which is dy dt. Does that make sense? Dy du rather. Does that make sense now? Okay. So by the time you take this, which is dy, since y is cos u. Does that make sense? So by the time you differentiate that, you are going to get minus sine u. Okay? So by the time you bring this guy, du dt and this, you are going to get dy dt, which is our function that we're integrating, differentiating. So this becomes, the cos omega t becomes the sine minus sine u. Is that okay? Dot this guy, omega. Alright. Now if you do not get what I did, just comment in the comment, put down in the comment section below. I'm going to be explained in my ACOP series now. In the ACOP series, ACOP stands for anybody can understand physics. Is that okay? So I'm going to be breaking down basic terms that people find hard to understand in physics generally. So if this is the case, then we have the minus omega minus omega sine u, and u is omega t. So minus omega sine omega t. That's the answer to our derivative there. Okay? So if that's the case, then we'll have that E will be equal to minus NBA d, so times this, dd becomes minus omega sine omega t. Okay? So if that's the case, then E becomes minus times minus plus, so NBA omega sine omega t. And that becomes our equation for induced EMF. All right. So EMF induced is going to be equal to all of this. All right. So now, let us discuss what is known as back EMF and eddy currents. Back EMF and eddy currents. Now, what is back EMF? Back EMF is basically the concept of electromagnetic induction that we just discussed, which is this guy here is a back EMF because it always opposes the change in magnetic field that produces it. It causes current to flow in a direction that opposes the change in magnetic field that produces that EMF. And that's what back EMF basically is. That's what back EMF basically is. So back EMF leads to the generation of what? Eddy current. Back EMF leads to the generation of what? Eddy current. Now what is eddy current? Eddy current is a current that is induced by what? A changing magnetic field in a coil of wire. In a coil of wire. Another thing is also that back EMF can also be induced in a rotating coil. Because if a coil is rotating in a constant magnetic field, or we call it uniform magnetic field. So by the time it's rotating, if you remember our concept of motor effect, where we talked about the fact that you use a split ring in order that coil of wire may not rotate in the reverse direction. Okay, so in that case, so we use a split ring. We're also going to get to generator. Is that okay? So you understand one of what I'm talking about, rotation. But my point is that back EMF is induced because of the rotation in that coil, the rotation of that coil. So as that coil is rotating, it's inducing a back EMF that is trying to, hinder the change in magnetic field that is produced, that is creating the EMF. Is that okay? So we call that back EMF. And the current induced there, due to that back EMF, is called eddy current. Now, some things that you should know about eddy current is that it only flows in a loop. So there has to be a coil. There has to be a coil. Is that okay? For eddy current to flow. It doesn't flow through gaps. Is that okay? It flows in a loop. In a loop. All right. So in a circular path. So it flows in a circular path. Another thing is that it causes wastage. So you see that heat is generated. Is that okay? Heat is generated. Heat generated. That's due to eddy current. Due to eddy current. So, and some of the application of the use of eddy current, some of the application of eddy current basically is in our speedometer in our automobiles, in our cars, speedometers. Is that okay? Okay, so that's that about eddy current and induced EMF and all. Now, where are the applications of this electromagnetic induction? Now, one of the applications is in generators. Is that okay? Before we consider generator, let's consider transformers. Transformers. So what are transformers? A transformer basically is a device that can either increase voltage or reduce voltage. So what does it do? Is that we say is that it steps down voltage or step up voltage. Is that it steps down voltage or step up voltage. And for a transformer that steps down voltage, we call it a step down transformer. And for one that steps up or increases voltage, we call it what? A step up transformer. Now, this is the basic structure, that I call it structure of a transformer. Okay, so now this is a transformer. Now, this coil of wire on this side is called the one that is connected to the AC source. This is our AC source, alternating current source. And this is our load. I just put a bulb there, is that okay? So this is our load. The load, or you call it that's the load, yeah, basically. So this one that is connected, this coil of wire that is connected to the AC source is called this coil of wire is called the primary coil. And the one that goes to the load is called the secondary coil. The one that comes from the AC source is called primary coil. The one that goes to the load is called what? The secondary coil. Okay, if that's the case. Now look at this. The power in the primary coil is called P sub P. And the power in the secondary coil is called P sub S. We also call it power out input or power, and here we call it power output. Is that okay? Now this is the case. If the coil in this primary coil or the input coil in the input power source, if the coil is more than the coil in the output, we are going to call that a step down. Voltage here will be higher than the voltage here. Think of it that way. Because there are plenty coils, more voltage. Okay, I probably didn't mention this. Now, the EMF that is induced in that our electromagnet that we talked about at the beginning of this video, the EMF that is induced, it can be amplified or increased if you increase the number of turnings on this coil, or you increase the strength of the magnet. The first thing, increase the coil of the wire, or the strength of the magnet, or the speed at which one of these, of the relative motion of one of this, of the system. Is that okay? Whether it's of the magnet, you increase the speed at which is coming and going back. Is that okay? You are going to, in that way, increase the EMF. So we said, now if the number of coils in the primary coil is greater than the number of coils in the number of turns in the secondary coil, then that is a step down transformer. So in a step down transformer, you expect that the voltage that is entering here is the voltage here is greater than the voltage that is going to the load. Is that okay? So in most of our homes, we use the step down transformer because on the electricity cable that brings light from the source, that brings power from the source, is it comes at a very high voltage. So what you want to do is that your appliances are rated with low voltage. Is that okay? As low as 220 or to 240 in Nigeria, for example. So you have to step it down. Is that okay? Because something that is coming at about 13, I think in Nigeria we have 33 kilovolts power cables. Is that okay? So those power cables, that's why in fact you see them, you hear them vibrate when you are walking under them because of the amount of voltage that they are carrying. So, and that's when we transmit electricity here. We transmit high voltage. I've mentioned that before. Low current, high voltage, low current. That's why it's able to go long distances. So my point is that the one that enters our house, we use a transformer to step it down. So the number of turns in the primary coil that is coming from the source will be greater than the number of turns in the secondary coil. And if the opposite is the case, such that the number of turns in the primary coil is now less than the number of turns in the primary coil, then what we want to do is what? We want to boost the voltage or amplify it or increase the voltage. We call it a step-up transformer. Step-up transformer. All right, now, for an ideal transformer, which does not typically exist, in an ideal transformer, the efficiency of an ideal transformer is 100%. And if the efficiency of an ideal transformer is 100%, then it means that the power from primary source or power in the input will be exactly equal to the power in the output or primary power in the secondary coil. Is that okay? And if that is the case, it means that it exactly means that you know that power is equal to current times voltage. In this case, current in primary coil times voltage in primary coil, or EMF in primary coil. Either way you see it. Is that okay? Then power in secondary coil will be IS times EMF in secondary coil. So if this is the case, it therefore means that power in primary coil, let me create a clean sheet here. So we have that if P sub P is equal to P sub S, then IPEP will equal to what? ISES. And if this is the case, it means that IP, if you divide both sides by IS, you have over IS over IS. And if you divide both sides by EP, let's divide both sides by EP. So we have IP over IS is equal to ES over EP. Does this make sense? All right. Or also recall that the number of turns is directly proportional to the EMF. The EMF here is high because the number of turns is high. The EMF is low because the number of turns is low. So EMF, number of turns is directly proportional to the EMF. So if that's the case, then we therefore have that N sub P is directly proportional to what? E sub P. So that N sub S will equal to what? Directly proportional to what? E sub S. So that N sub S over N sub P will equal to what? E sub S over E sub P. And if this is the case, therefore, then N sub S over N sub P will be equal to what? N sub S over N sub P will be equal to what? I sub P over I sub S. Alright, so these are so many equations for one thing. And one thing you will know our channel for is that we generate a lot of equations that are necessary, that you will need. So, and we teach you how, that's why it's called the formulaic approach. We teach you how to generate those equations. You see, it's not hard. So far, we've not done anything hard. Is that okay? So if this is the case, so this is the case for an ideal transformer. But for a natural, when I say natural transformer, a non-ideal transformer, let's call it that name, non-ideal transformer, which is a transformer that we all use, the efficiency is not always 100% because, come to think of it, it's a machine. So no machine is 100% efficient. So the efficiency is not always 100% efficient. So the efficiency is such that the power in the output over power in the input times 100. Is that okay? So we say P power in the output is what? P sub S over E efficiency is equal to not EMF. Efficiency is P sub S over P sub P times what? 100. Is that okay? So that is the efficiency. So it means that there's going to be a loss in power. So what's going to be the loss in power? It's just a P sub P minus P sub S. For a case where the EMF in power in input is greater than input is greater than power in output. All right. So that is the case for transformers. So now let's now get to the business. Generators. So a generator is one of the application of electromagnetic induction. A generator. I think I should clean this. So, what is a generator? Now, a generator practically is something that we use to generate electricity. That's the simplest definition for a generator. Oh God. That's the simplest generator. Okay. Is it bright? Okay. So that's the simplest explanation for what a generator is. We use it to generate electricity. And it is such that, just like we have in motors, we're going to have a magnet, a permanent magnet that looks like this. Okay, so this might be our north, let this be our south. Okay, so what we want to do with these two magnets is we want to generate electricity. So now we have found out that is a changing magnetic field or changing magnetic flux that creates electricity. So let's show that in concept or in context rather. So in an AC generator, we use slip rings. Is that okay? So a ring is going to be connected here. A ring is going to be connected here. And a carbon brush or carbon brushes will be connected to that. Another ring will be connected here with carbon brushes firmly connected to that. And I have told you before, there is a reason why we use rings. The reason why we use rings is so that there will be no tangling of the wire when rotation begins. Is that okay? Okay, so they will connect our load here. Let's just put load. So we want to generate electricity in this thing. So what happens? So we're going to connect this to a particular drive or driver. Something is going to cause rotation here. So in our hydro power system, we use turbines. Is that okay? So let's call this our turbine. So when wind, it could be wind turbine, it could be water, hydro turbine, whatever that is called. And that is the one in which water drives. So if it were wind that drove this, so once wind causes rotation of that guy, once the wind causes this guy to rotate, this guy will begin to cause a rotation of this guy. So as this system begins to rotate, it will be sliding. Notice it will not tangle. It will not tangle up the wire. It will be sliding on the wire. It will be as I sliding. It will be, of course, basically touching the carbon brushes. The carbon brush there is to maintain. The carbon brushes there are to maintain contact. Is that okay? And the slip rings are to, bring about, make sure that there is no tangling of these wires. So these are conductor wire, and these are our load, and these are our armature. The armature is the guy that is rotating. Armatures are usually more, not one loop. Is that okay? The loops are more, and these are our stator. The magnets are the stationary part of it, so we call them stators. All right, so the point is this, that this guy begins to rotate. So once this guy begins to rotate, here's what happens, okay? Let's say this thing was driving it in the clockwise direction. So if this was being driven in the clockwise direction, so at a particular instance in time, this guy will go down. Does that make sense? And at that instance, where will this guy go? This guy will go up, okay? We know direction now. Now, we know direction of the armature, but what direction will the current flow? So that is where the Flemings, Mr. Fleming, is that okay? Was my friend in primary school. Okay, so Fleming's right-hand rule comes to play. Remember, Fleming's left-hand rule, we use it to find the direction of movement of the armature itself. Now we know the direction of movement of armature, because in that one we know the direction of current because it's connected to an AC source or DC source. So we know the direction of current. So since we know the direction of current now, we only need to know the direction of movement or rotation of the armature. But in this case, we already know the direction of rotation of armature due to this wheel or that is driving it. Is that okay? So with that one, with this one, we want to know the direction of the current. So we use the Fleming's right-hand rule to know the direction of current. So, and it is like this. Let me just come to the screen without drawing. Now, if this, so your hand should be oriented in such a way that they are all at 90 degrees to each other. So, for example, I will orient this guy and this guy in 90 degrees to each other. You see this 90 degrees, right? 90 degrees, if you look at it, 90 degrees. Then I will orient this guy and this guy in 90 degrees to each other. If you look at it, it's not so perfect, but you know, kind of like 90 degrees. Okay, then I will orient this guy and this guy and this one. That is this middle finger and this one. Is that okay? Hey, that's going to be what, 90 degrees. Okay, so I will orient all the three fingers to be at 90 degrees to each other. Now here is the case. Now you see, this hand here is the direction of movement of the armature. Is that okay? Our conductor that is in the uniform magnetic field. The direction is the direction of armature. The direction of this is going to represent the direction of our magnetic field, which is in this case from north here to south there. From north to south. I'm going to draw that out later. And this one, this is not middle finger. All right. This one is going to be the direction of current. Is that okay? So we now have what looks like this. Is that okay? So now let's arrange it so that it tells us the direction of current in this system. Remember, motion is down on this side. On this side I'm pointing at. So since motion is down, then let's bring this hand to face down. Okay, so we are correct with that. Magnetic field is from north to south. So let this guy face that direction and down. Then where will be the direction of current? The direction of current will be into the screen. Let me go out to go and do it now. So magnetic field is going from north to south. So that's north to south. This part is moving here. So current will be moving out of the board towards you, right? So it means that current here is going to be moving downwards. And the opposite is true for this guy. On this other side, this side where the arrow is going up, on this armature, magnetic field is still north to south, but force is now up, right? Because the guy is moving up, okay? So where will the current flow? If magnetic field is still like this and force is up, then current should flow upward. Does that make sense? Let me show you that again. I said since this guy is going up, magnetic field is still going like this, where will current flow? Into the board, or like this. So do you see that? Okay, so now since this is a slip ring, not a this is a slip ring, not a split ring, what will happen is that the direction of current will always reverse itself after 180 degrees of rotation. Does that make sense? Yes, it makes sense. Very simple. Once this guy, you know, current was going up like this, in this side, on this side of the wire. By the time you flip this side of the wire to this place, right? Current was going up on this side before. By the time it comes here, you know it will be going down. Current will now start to go down. Is that okay? So direction of current will now be such that you have something like this and like this and like this as this thing is rotating. Does that make sense? Okay. If you don't really understand, make sure you check the video on motor. I really used a device to explain that part very well. Okay. So that is the Fleming's left-hand rule. And that's the generator effect of electricity. And of course, this system we drew here is an AC generator. So we could also have a DC generator. In a DC generator, what do? We simply change the slip ring to split rings. Is that okay? The split ring does not split anything. No? And what it does is that it doesn't shatter anything or whatever. What it does is that it changes the direction of the contact so that at every 180 degrees rotation, the contact between the ring and the carbon brushes change. Is that okay? So that the current does not flow in different directions. So there will be a point of no connection. There will be a point when it's rotating that there will be no connection. Just make sure you see the video in the description below. I have explained the concept of split ring and slip ring too. Is that okay? In slip ring, there is connection all the time, so the current will be alternating based on the direction of movement of the armature. Is that okay? So that is the application of electromagnetic induction. The second one is, the third one rather, is the induction coil. Now, induction coil is basically the coil of wire, is that okay? Coil of wire that creates induction, electromagnetic induction. And there are two types of inductance. Inductance simply means an opposition to the flow of current. Opposition to the flow of current that is created as a result of what? Changing magnetic flux through a coil of wire. Is that okay? So, there are two types. We have self-inductance. That is the one that we have seen so far in the system. But the other one is mutual inductance. So we say we have self-inductance or self-induction, and we have mutual induction. Now, with the mutual induction is one where EMF in one induction coil is causing a change in another induction coil. So that is mutual induction. Is that okay? And because of that, because of induction, energy is stored in the induction coil. And the energy stored is given by the formula 1/2 Li squared. Also, the arrangement of your induction coil in your circuit also determines, the kind of the current that will flow there. Is that okay? So we have two types of arrangement: the parallel arrangement and the series arrangement. In the parallel arrangement, you have an induction coil to be like this. They'll be separated by junction, just like with resistors. Do you remember? So this parallel arrangement, this L1, L2. And in series arrangement, you have an induction coil to come in sequence. Is that okay? Or serially, one after the other. This is L1, this is L2. So to calculate the total inductance here is going to be, total inductance here is going to be 1/L equal to 1/L1 plus 1/L2 plus 1/L3, blah, 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 until you go like that. Now, and in series, we have L1, L equal to what? L1 plus L2 plus L3, blah, 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 as we have it that way. So, this will be the end of, no. I've solved some questions on this induction and inductance. So I'm going to link them in the description below so that you see how I solve questions so that it will not elongate this video again. What I'll just do is in other videos too, I'm going to be starting an ACOP series. So please, if you don't if there is any concept in O-level physics, or college physics that you don't understand, just do well to link them in the, comment them in this comment section below, put it in the comment section below, and I'm going to add them to the ACOP series. I already have a set of concepts that I want to break down. ACOP stands for Anybody Can Understand Physics. Is that okay? So do well to follow that series. God bless you as you subscribe to the channel. Please I've been shooting since morning. Try and just subscribe to the channel. It makes me understand that you are enjoying the content I'm posting and you are gaining value. God bless you as you do so. Amen.